class, and welcome back. So in this next unit, we're going to be jumping into kind of a new application of all the ideas that we've been studying all semester long. We're really going to be revisiting over the next few units everything we've done since the beginning of the semester, but now we're going to apply it to things that are rotating while also translating. The physics gets a little trickier, but it's really the same tools that you've been learning that you're going to be applying. So to introduce you to this idea, I want to start with a few demonstrations. I have before me a ramp. So far, anytime we've dealt with ramp type problems, we've only looked at things translating down the ramp. So everything in a frictionless world without air resistance should move down the ramp at the exact same speed. So now let's see what happens for things that are rotating while also translating. I have a ramp here, as I mentioned, and I have various different shapes. So I have some solid cylinders of different masses and sizes. These two happen to be the same mass. These two are different masses but the same radius. I also have here some hollow cylinders with similar radius values to the others, or similar masses depending on which two, like these have the same mass. These are the cylinders. And then I also have a few spheres. I have a solid sphere and a hollow sphere. So we're going to see how these various shapes, these various geometries and masses compete or race down the ramp. I think I will start with two solid cylinders of the same size but different mass. So they're both solid cylinders. They both have the same radius. Let's see which one gets to the bottom of the track first. Oh boy howdy. If you noticed, they should have, and I believe did, go down at the exact same speed, getting to the bottom at approximately the same time. There might be a little bit of influence of air resistance and non-uniformity in the boards, but if we ignored those effects, they would have gotten to the bottom at the exact same time. So now I want to do another race, looking at, since the radius seems to not matter, I wonder what effect mass has to play. So now we have two cylinders here, as I mentioned earlier, that have the same mass, but different size. Let's race with these guys. Again, these are both solid cylinders. Now this is going to look a little funny, but I'm going to angle my meter stick a little bit so that they release at the same time as best I can. So we get them going. Oh, there we go again, same time. So the solid cylinders, I could do it all different ways, as many different combinations as we want. They'd always get to the bottom at the same time. So some of you might be thinking, okay, well, isn't that what you said was like how everything acted previously when things weren't even rotating? Does everything just get to the bottom at the same time no matter what? Well, let's see what happens once we introduce some new shapes. So here now I have two cylinders of the same radius. They're different masses, but we already established mass doesn't matter. But one is a hollow cylinder and the other is a solid cylinder. So let's see what happens when we race these two. Oh wow, those definitely did not get to the bottom at the same time. The much lighter hollow cylinder went much slower. So some of you might think it's about mass, but we already showed mass isn't the main contributing factor. In fact, the mass won't matter. It has to do with the type of shape we're dealing with. Now to fully understand this and to problem solve with this, in this unit you're going to be learning lots of different things about rotational motion. You have to understand what is rotational velocity, what is rotational acceleration, what is the relationship between rotational motion and translational motion as something is rolling and moving at the same time, and how do we problem solve with these things. You're going to find the tools that we learned early on, like our kinematic equations, super helpful. You can use the same principles here as well. You're just going to be combining these different ideas with the new information we're learning about rotational motion. But the cool thing here is what we find, the only thing that matters in these races is ultimately the type of shape we're dealing with. So to drive this point home, I'm going to do one last race. I'm going to have three items that all have the same radius and approximately the same mass. We have a hollow cylinder, a solid cylinder, and a solid sphere. And we're going to race them. And even though they're the same mass and the same radius, the only thing that's going to affect the time they get down is the type of shape they have, because it's actually about the mass distribution. The things that have the mass furthest away from the center are going to go the slowest because they have the most rotational inertia. They have the most resistance to change in rotational motion. So the thing with the mass nearest the center on average is the sphere. The next is the solid cylinder, and then all the mass on the hollow cylinder is furthest away, so it's going to have the most inertia, and therefore we'll get to the bottom last. So if I line these guys up for one last race, we get it set up. 3, 2, 1. Oh, look at that. Might have been hard to see, but the sphere was first, then the solid cylinder, and then the hollow cylinder came in last. So you'll be unpacking and learning all the physics and the rules and the equations that govern these things in this unit. Get excited and have fun.